Welcome to my presentation about Monix observable implementation. I've had the pleasure of speaking at ScalaMatsuri last year, and I'm delighted to meet with you again, even considering the not ideal circumstances. Yeah, my name is Piotr. I come from Poland in Europe, and I contribute to open source as a hobby. And I'm mostly active in Monix, but I also contribute to other Scala libraries from time to time. The Monix is a library for asynchronous programming, and the scope is quite broad. We provide quite a few data types and many concurrency utilities for both future and CATS-effect compatible types. And if you're familiar with CATS-effect, FS2, or Monix, or Zio, then Monix is a library in a similar space. Some modules are meant to be used together with those libraries, and in others we provide competing implementations. And in my opinion, the unique feature and distinction of Monix is our approach towards impure code. We want Monix to be a great fit in both purely functional code bases and those that would rather mix it with some future or akka-based code sprinkled here and there. And we fully support such use cases rather than just pushing towards one particular style. So this is something that some people may like a lot and some others not so much. And in this presentation, we will talk about observable in particular. And it is a streaming data type that is inspired by ReactiveX, but with a much stronger functional influence. If you're interested in Monix observable origins, then I recommend the presentation by Alex Nedelcu, who is the library's original author. I won't be going into it in this talk. And so this is a small example how observable could look like from the user's perspective. So the API is quite declarative, high level, and similar to what we can see in other streaming libraries like FS2. However, the internals are not pretty at all, and that will be the focus of the talk. So from now on, we'll dive deep into messy, low-level details. So please keep in mind that most of them don't concern regular users and are only relevant for contributors. So if you're just a user, the code will mostly look like the slides I showed earlier, rather than what we're gonna go through in the next 30 or so minutes. And the basic building blocks are observer, subscriber, and observable. And the observer interface defines three methods that are called whenever there are specific events emitted by its source. And the subscriber is an extension of the observer that adds a scheduler. The scheduler is a Monix implementation of execution context that adds some scheduling functionalities, and we use it for any concurrency in the operators, or if we would want to map the future here. And if we didn't include it in all observers, using this subscriber trait, then we would have to pass scheduler for each operation that has any concurrency or does anything with this future. But if we have this constraint that we always have access to the scheduler, then we only have to pass it once during the subscription so that that can make for a better user experience. Okay, and in other words, and I skipped one. Okay, so, and last but not least, there is an observable. So subscriber can subscribe to the observable, and upon subscription, observable starts emitting events to the subscriber. So in a sense, it's like an unsafe run on I/O. So until this point, the observable is purely functional. And in this relation, the observable is the producer of the data and subscriber is a consumer. And in other words, so if the observable is the source of the river, the observers could subscribe to the stream. and then the observable emits events by calling onNext or other these calls on the observer. And all observer implementation need to follow the specific protocol. And first of all, the onNext can be called 0, 1, or multiple times until there is either incomplete or an error, at which point we are no longer allowed to send any onNext event. And you see that onNext can return the future of ACK, and where ACK stands for acknowledgement. And it can be either a continue, a stop, or an asynchronous operation that will eventually return like continue, stop, or a failure. So if we receive a continue, we are allowed to send a new onNext. If we receive stop, we are not allowed to send any new events, and we need to stop immediately. And if we receive the future, so asynchronous acknowledgement, then we need to wait for its result. So with operation like map, so this gives us back pressure. And for on error and on complete, we can only call one of them, so not like both on error and on complete. But in this case, we are not required to obey this back pressure. So if even if the last onNext is asynchronous, we don't have to wait for the response. Finally, all calls to these methods must be ordered and they can't throw exceptions. We'll come back to the former point in one of the examples. And the full protocol with more detailed description is available in the documentation. And as you probably noticed by now, a lot of complexity lies in the implementations of observers because we have to obey this protocol. We have a test suite for a lot of these points, but still it's pretty delicate and needs some attention. And fortunately, as a user, you don't have to deal with it often. Even if you want to write your own operators, you can do it by composing existing ones using a much safer and higher level API. And implementations of observable only need to implement unsafe subscribe method, and which is then a cancelable that lets us cancel the source from the outside. And unlike stop here, the cancellation is not immediate. It is on a best effort basis, like cancellation in Monix task or cause-effect.io. And that's it from the rules. So, and hopefully everything becomes clear with examples. And here's an implementation of a simple observable that emits an element of type A and then completes. So upon subscription, we call onNext and on complete one after the other, so which is legal according to the protocol, as I mentioned earlier. And then we return the cancelable empty because there's not really a way to cancel these calls. And in case of subscriber, we need to implement these three methods and also provide a scheduler. So here I just use scheduler global. In general, I think it's not the best idea. You would pass it as a parameter, which is usually the case in operators that don't send any events downstream. So we actually later we'll see an example how we can, for instance, extract it from a Monix task. And in onNext, we print the element and then return continue synchronously to signal that we are ready for more events. And to combine our observable and observer implementation and execute it, we can see this results printed in the comments. So we'll receive 10 and final event. And so this code snippet shows the same example, but with everything inlined. And so this is the full code that we'll be running. We don't even need, so you can notice that we don't even need Monix to write this stream if we replace scheduler with something else. So there are no extra materialization interpretation steps or piggybacking on an effect type like task. So the observable is fully capable of executing on its own. So I think that's a key difference between the observable model and the other popular streaming libraries. So if you want to have a deep understanding of observable, you only have to know the implementation of operators that you use. And as we will see, they can be very complicated, but you can always attempt to understand them in isolation. And another point I want to note, so despite on next returning future, our this code is actually fully synchronous. So we don't go through any overhead of having future. Okay, so I really hope that you could follow the implementation so far, because now we'll tackle a bigger example. So we'll write a stream that repeats a provided effect in a loop for a specified duration, and then combines all the results in a list. And we also want to be purely functional and provide an API that won't require users to write their observers or to subscribe manually. So we want all of that to be taken care for us. So first of all, the repeat eval returns an observable that evaluates the argument in a loop. So in terms of API, all we have to do is put it as a method on an observable companion object. And to implement the observable, we have to implement this unsafe subscribe method. And there are two extra concerns that we need to consider. So the subscription could be cancelled with this. And if it happens, we need to stop producing elements. There's also a concern of fairness. So if we evaluate this effect in a synchronous loop, we might end up with a situation that we take the thread forever, but there might be other parts of the application that would like to execute on the same thread pool. And in many cases, it's good to reschedule the computation from time to time to prevent such situations. The scheduler includes several execution models. So we can iterate synchronously, reschedule the computation per n iteration, or reschedule it on each iteration. And if we choose to do it per n iteration, then we will have to keep track of the index. So we need to add this parameter. And our loop implementation goes as follows. So first, we evaluate the argument and send it downstream. And this argument is lazily evaluated per each iteration and its user input, so it could throw an exception. That's why you need this try catch to protect against this. And then we need to decide whether we should reschedule the computation or not. And here 0 means that we should reschedule. So if it's 0, then we reschedule. And anything greater than 0 means that we should just continue on the same thread. And anything less than 0, so that it won't enter this loop, means that we should stop producing. And I didn't include the next prime index implementation, but in the case of synchronous execution model and always async execution model, it just returns constant values. And in the case of batch execution, it increments the index, divides it by the batch size, and then returns the remainder. And also note that if downstream returns the stop here, and which we check in this moment, then we stop the source immediately. But if it is cancelled with this boolean cancelable, we are not required to act immediately. So in this case, we only check it during asynchronous boundaries. And if the result of onNext is the future of something, so asynchronous result, then we have to wait for it asynchronously anyway, so we reschedule as well. And for a reschedule implementation, we just use the onComplete on the future that handles all the detail for us. Okay, so that's the repeat eval, and for combining for our toListAll method, we need actually two pieces to implement it. So one is a method that will transform an observable of many elements into an observable of a single element that is a list of all emitted elements. And we can express it with fold left. So we could just implement this operator and then use it here to do our transformation. We use this mutable list buffer just for the optimization purposes. And the other piece is a method that will subscribe to the observable, take the first emitted element, which will be the list of all elements, and then return a task with all the results. And to transform a source observable into another observable, we actually need to write a new subscriber that will subscribe to the original source and send some transforms event downstream. And first of all, we need to evaluate the initial state, and this is user input, and we always make sure that we also consider the case where user input can throw some exception. So, but not the stream errors flag that is quite common in our implementations. So if evaluation throws here, then we catch the exception and like send the error downstream. But if the error is from after this point, so somewhere here, then that would be a breach of protocol, and this has undefined behavior. So we don't want to call on error in this case or catch an exception, because it might have already happened there, and we don't want to make it worse. And here's the implementation of our fold left subscriber. So now, first of all, note that the scheduler is already available to us from the argument of subscribe. So we don't have to summon it like from nothing or pass it as a parameter. We have it already available, because whatever subscribed to us, it needs to have it. And we use two variables. First is done flag, and it is necessary because our onError can be called in two ways. Either from our onNext here, if the state transition throws an exception, or if upstream calls onError or onComplete. And since it is not necessary to back pressure on final events, you might have a situation where we call onError here due to the failure in onNext, and upstream calls onError or onComplete without checking the last result, just like we do ourselves in our onComplete. So this flag is necessary to protect against this. And the state variable is needed to keep track of the state that is updated with each onNext event, and then it is emitted on complete, so we only send one element downstream. Okay, and you might be wondering if it's okay to define these variables without any synchronization. So because if there are any asynchronous boundaries, like due to scheduling in repeat eval in the source, and then they could be accessed from different threads. But fortunately, they are guaranteed to be always up to date, regardless of the thread. And because of back pressure requirement in the protocol, we always have to wait for on next result before sending a new one. So if it's synchronous, we don't leave the threads, so there aren't any synchronization concerns. But if it's asynchronous, then we need to map the future in some way, just like here. And if future reschedules on each operation, the details will look like the snippet on the side. So we define the variable on one thread, and then we schedule a runnable to run on a potentially different thread and modify the variable. And finally, on that thread, we schedule yet another runnable and read the variable. And this actually establishes, happens before relationship. So these operations are guaranteed to see their updates according to the Java memory model. And so this is very nice consequence to this, because we often don't have to synchronize the state in the operators at all. So the observer protocol adds a lot of complexity to the implementation because we need to follow it, but it also gives us some extra guarantees that we can use for optimizations. Okay, so now we can use fold left to gather elements in a list. And so what about returning a task that we complete after the list is ready? And fortunately, there is a task constructor that lets us create it from a callback, which is a perfect fit to implement subscribers. Furthermore, we even have access to the scheduler that will be propagated through all subscribers, as we saw earlier, because we also need to provide a scheduler if the task is running. And the implementation is quite straightforward. We completed the task on the first element, and the set is done flag to true. And this flag makes sure that we don't complete the task more than one time by mistake. So note that until this point, there was nothing specific to Monix task about what we've seen in the stream. So I think it could be interesting to see like how we could do the same thing, but with a different effect. And so here as a bonus, I included a Zio implementation, which is pretty much the same to task. The only inconvenience is that it doesn't have access to Monix scheduler, but it does have access to a different one. So like we can create it and still have, or we could just bite the bullet and pass it as a parameter. So also there is nothing about Monix task here. It would be possible to have native support for all available effect types if there was a demand, even without going any type classes. And the last operator that we'll look into is take by time span, that will take the elements for a specified period. And one way of implementing it is to redirect all events without any changes, but run a concurrent timeout task that will stop the source gracefully when it's time to do so. And as before, we transform the source observable by subscribing to it with a new subscriber, and we get scheduler for free. And now we have to add this concurrent operation that will stop it. Okay, so we can take advantage of the scheduler and use it to run our task after a specified time span of the schedule once operation. And once it runs, we can call onComplete. Also note that we create this composite cancelable that contains both the subscription and the concurrent task. So if the subscription is cancelled, we also want to cancel the timeout because it is no longer relevant. Well, we can just call onComplete from this task. We need to make sure it is not called twice and that we don't accept any new elements afterwards. And we could handle it with isActive flag. So if there is a stop or an error from downstream, if there is an error or completion from upstream, then we check the flag. If the source is still active, then we deactivate it, set the flag to false, and cancel the timeout. And one catch is that in this case, we have to synchronize access to isActive. So as we saw before, synchronization is often unnecessary, but we need to do it if there is some extra concurrency related to the given operator. And our concurrently running timeout task is not tied to back pressured on exchange, so we don't have any guarantees here. Here's the updated code. So I have just added synchronized everywhere. I think I also should add it here, but I missed it in case this is asynchronous. So now also let's briefly cover two optimizations in this operator that we can make. And the first one is a synchron stop or failure called here. That until now remained a mystery, but here's the implementation. So it calls this callback if there was a stop or a failure. So first we check if it's available synchronous response of stop or continue, which helps us avoid unnecessary asynchronous boundaries on our fast path. And if the response is asynchronous, we have to check the result with onComplete here. So this prefix sync is because we want to go synchronously if we can, and if we can't, then we have to do asynchronous boundary, which has some performance impact. And the second optimization is that we can save some allocations if our subscriber is also runnable. So it will sort of schedule itself. So earlier we defined a new runnable object to be scheduled. But instead of having both runnable object and the subscriber object, we can have one object that is both. And then we only need to add the run method to the subscriber directly. And when for this timeout task, we schedule this, so ourselves. I think it's also quite common in implementation of effect types like Monix task. So if you were ever wondering about this. And here's the final implementation of the operator. If you'd like to see how everything fits together. So there is quite a lot of noise with optimizations and having to obey the protocol, but it's still not so long. And I hope you can understand why some things are done like that. Okay. And finally, we have everything we need to write this example. And if we inline it as we did before, we can see everything that is going on. And if you can understand these operators, you will know everything about the code that's running. So entire complexity is in the operators, but the glue that ties everything together comes for free. And I want to take this moment to emphasize that if you're a regular observable user, you won't see this unless you really want to. So even if you want to write your own operators, I would recommend starting with composing already existing ones, like these ones, and using them, like composing them to write another one. And then if you maybe want to have some extra performance gains or just like low-level code, then you can try to do it like we did in the slides. And there's more to observable operators, and those are the most notable areas that we didn't cover in the presentation. However, I'm confident that once you grasp this presentation's contents, you will be able to understand also this other operators code. Because the talk has already covered most of the patterns that we use to either obey a protocol or for optimization purposes. So if you're able to filter through that noise, then it will be easier to just understand the actual logic of the operator. And I know if one day I might do a sequel to the presentation and cover the rest if you like it. And also, so if we compare the implementations of the to the operators of competing steering libraries like FS2 or Zio, the observable is like sort of on a lower level because in that libraries a lot of even operator implementations are purely functional. So if you're familiar with this style of code, they can be much easier to reason about. And a big reason why we use such dirty internals is performance. And so I will go through a few benchmarks very quickly just to show you what kind of gains our model can provide. Just keep in mind that benchmarks can be wrong for many reasons, and also I don't believe the performance is the best criterion for choosing a library. So my general advice is just not to trust the benchmarks in general, and definitely don't trust the benchmarks that come from someone involved in one of the libraries, so like me. Okay, so the first scenario is just map filter sum from a collection that already exists in the memory. And Zio and FS2 streams are pool-based and operate on chunks, so like a buffers internally. And for the benchmark purpose, I have already provided them with chunked data. So the amount of elements and the results is the same as in these cases. But other implementations process elements one by one. And you can also like just compare the API of the libraries here, and also added some Scala collections to see what kind of overhead we introduce, and also like an iterator with fused while loop just for fun to see how fast actually we could go with this specific scenario. And those are the result. And so note that how in this case the Monix observable seems to like handle this even faster than collections API. And so, but still it is nowhere near close to a fused while loop. Writing code in this way could quickly become nightmares, and observable and other similar libraries provide a high-level API to solve complicated problems that could be better in a longer run. And so I have quickly just the operator, so map accumulate, is similar to fault, but it emits each intermediate state. And so here I am actually positively surprised by FS2 result, which comes quite close to Monix. And I'm saying that because it can be pretty difficult for a pool-based model that also has purely functional internals that are, like, I think, way easier to write and read. So that's actually pretty good. A merge is a concurrent operator that takes a stream of streams and then merges them concurrently to a single stream. And I doubt that this operator would be a bottleneck in your application, but like this orders of magnitude differences can sometimes add up. And the last scenario is similar to the first one, but we also compare the buffering cost and introduce a lazy boundary with an effect like Monix task per each batch. So here I just included how it would look like FS2, for example. So we start a stream from some collection of elements, and then we chunk them to some chunk size in one scenario, and in other we already provide these chunks right away, so we don't have the cost of this chunking. So this scenario would be like if, for instance, we're using some FS2 based library that already does it. And then we evaluate some effect for each batch and these operations. And so I didn't include buffering in Zio's case because it won't do any buffering if we create the stream from a collection that already exists in a memory. Instead, it will like access that collection directly in its chunks, from what I understood in the implementation, which is actually very cool optimization. So, and in cases when this optimization can happen, it can give like really good results. So in this benchmark, it's even faster than observable if we also have to do the buffering. However, if we operate on prepared chunks of elements, then like observable gains a big advantage, or in cases where it's not possible to use this one. Okay, so let's summarize what we've learned and come up with a few conclusions. So as we experienced, the internals are dirty, and there's a lot of complexity in the operators. And also observable uses a push model. It doesn't operate on chunks on buffers internally, which is the case in pool-based streams like FS2 or Zio. If you want a higher throughput, we need to use buffers explicitly. For instance, operate on observable of an array of bytes instead of an observable of bytes. And we didn't cover it, but there are parts of the API that are not purely functional. By default, each subscription to observable subscribes to a new instance of the stream, which is purely functional. But sharing a single stream between multiple subscribers is not purely functional by default. And it's possible to do it 100% pure, but beginners can be rightfully confused. Also, it's worth noting that the implementation of flat map is not stack safe due to model limitations. So it's not recommended to make infinite flat map recursive loops with observable. And fortunately, there is always a way to express it differently. So let us know if you stumble upon the issue, and we'll help you out. And as for the good consequences of the design, the dirty internals provide a very low overhead for most operations and best-in-class performance. In some cases, observable can have higher throughput when processing elements one by one than other libraries processing in batches. We use a push model that is a natural fit for latency requirements, and observable is an effect of its own. It doesn't have to pay for the overhead of any run loop or interpretation phase. Last but not least, due to its roots in ReactiveX, there are tons of related resources from other programming languages relevant to Monix observable. Many Java and JavaScript developers are already familiar with RX, so if you're coming from this background, Monix can be a familiar choice. That is also a fantastic step into functional programming if you'd like to pursue it. And that's it from me. So thank you very much for attending the talk, and so thank you to the organizers.
ピョートルさん、発表ありがとうございました。それでは若干ながら、時間があるので、質疑応答をしたいと思います。そうですね、コメントで一つ、モニックスはハイパフォーマンスを意識して開発されているのですかねという、ごめんなさい。どうぞ。
Yeah, sure.
いいですか？
Go on.
モニックスはハイパフォーマンスを意識して開発されているのですかねという、コメントがありましたが、いかがでしょうか？実際そうなんですかね？
Yes, that's our goal.
はい、ありがとうございます。他何かありますかね？そろそろ時間が来ているようなので、これにて、終了したいと思います。もし、続き、はい、もし続きがあれば、懇親会などでお願いいたします。
So I just wanna say that, like, if there are any questions, also don't hesitate to contact me directly, either on Discord or on our Gitter channel. That's perfectly fine for me. I'm very happy to do so.
ありがとうございました。もう一度拍手をお願いいたします。ご視聴いただきありがとうございました。
Thank you, and thank you to the translators. I can only imagine how hard it is to go through all the code examples, and so big respect to you as well, and applause. Okay, so thank you, and see you around.